Welcome to my 10th ShowMe. This one is about solving systems of linear equations by graphing. Solving systems of linear equations is a really important application. It leads into a lot of complicated business problems that these days are solved by computers. But for the people who use the solutions and who use the software, it's important to have a basic idea of what the computer is doing. So this is where we begin that process. The challenge here is to find ordered pairs, sets of numbers, that satisfy more than one equation at the same time. Let me show you an example. Here are two linear equations in two variables. In the first equation, one of its solutions is the ordered pair 4, 7. If you put 4 in for x and 7 in for y, that first equation is true. But if I put those same two numbers into the other equation, it's not true. If I put 4 in for x, I'll have negative 2 times 4, which is negative 8, plus 6, which is negative 2. And that's not 7. So this point is a solution of the first equation, but not a solution of the second equation. The whole point of solving systems of linear equations is to find the ordered pairs that make both equations, in this case, true. When you can do that, you have found points in a particular space of options that you can use to solve a problem. X and Y could be lots of things. They could be two variables on a graph where you've measured quantities for a science experiment, and you want to find out where the two lines come together. They could be resources that you use to make a product, and so you've got to get two lines to come together so you know how to manage your resources to reach a particular result. In any case, if you can learn to solve this kind of problem, you've begun the process of learning how to manage multiple resources using a mathematical tool. That's a really valuable thing to know, particularly if you hope to manage resources in the future. So the challenge again, let's find the ordered pair of numbers that makes both equations true. As our title suggests, one way to do this is to graph the two lines. Let's take a look at what happens when we graph these two lines. The first line, y equals x plus 3, is in slope-intercept form. That means that we can find the slope by looking at the number in front of the x, in this case a 1, and we can find the y-intercept by looking at the constant, in this case 3. So 3 tells us that our y-intercept is 3. The line hits the y-axis at that point. The 1 tells us that our slope is 1. Slope, of course, is equal to rise over run. In this case, 1 over 1. So I can find another point in this line by rising 1 and moving to the right, or running 1. So there's another point also on the same line. And if we're careful about it, we can draw a fairly accurate straight line that imitates the behavior of our lines. So y equals x plus 3 is this first line. The second line, the slope is negative 2, and the y-intercept is 6. So we can go to 0, 6, and the line goes through this point. The slope is negative 2. So to find other points on the line, we go to points that we know are already on the line. We rise negative 2 when we run 1. Well, how do you rise negative 2? Go down 2, and then run 1, and that puts us right back on top of one of the points we've already found. Kind of takes the fun out of the search for a solution. Anyway, the other line looks something like this. Now, where am I going to find an ordered pair that makes both equations true? Well, each of these lines represents all the points that make one of the equations true. What we're interested in is the one point that makes both lines true. And there's only one point on the coordinate plane that does that. and it appears to be right there. That point is on both lines, so the numbers that represent that point, in this case 1, 4, might make both equations true. Before you just decide that it's the right answer, though, you should try both numbers in the equation. In the first equation, we take 1 times 1, that's 1, and then add 3, and we have 4. So, yes, it does work for the first equation. For the second equation, put 1 in for x. Negative 2 times 1 is negative 2, and negative 2 plus 6 is 4. So yes, it works there too. This point satisfies both equations. When you substitute the values in for x and y, you get two true statements. That means that this is the solution of our system. So, when you're looking for a solution for a system of linear equations, if you can graph them, the point where the two lines intersect represents your answer. Now, the graphing method is great for visually understanding what this all means, but I want to point out something about graphs that you have to be very careful about. Notice that I just didn't accept 1, 4 on the face of things. I still made sure that I put the numbers back in to see that they genuinely did work. I did that because your eyes cannot be trusted. Anybody who's ever experienced an optical illusion knows what I'm talking about. You can't just assume that because you think the two lines intersect at this one point, that what you see is obvious, that the answer is obviously going to be true. You need to take the answer you see and verify it in the equations. If you don't do that, you might find yourself tricked. Sometimes 2 and 11/12 looks an awful lot like 3, but it's not 3. So, it's very important that you understand. The graphing method is great, but you must verify every result because your eyes cannot be trusted, and your graphing honestly can't be trusted either. You're human, you make errors. So it's very, very important that once you've determined a possible solution, you put the numbers back into the equations to make sure that it really is a solution. Let's consider these two lines now. The first line, y equals 2x plus 5, has an intercept of 5 and a slope of 2. 2 can be written, of course, as 2 over 1. So to find other points, we rise 2 and run 1. So this should be another point on the line also. That line should look something like this. The line on the other side of the screen also has a slope of 2, but an intercept of negative 1. So it goes through the y-axis right here, and then again up 2 and over 1 to find the next point. So that line looks like this. Now it doesn't appear anywhere on our graph that there's an intersection. My graph isn't perfect. I'm not able to use a ruler, and ShowMe hasn't yet equipped us with a straight line tool. But there should be a suspicion here that these two lines might not ever intersect. In fact, it should be more than a suspicion. The two lines have the same slope. They're always going to go up 2 and over 1. And since both of them follow the same pattern, they shouldn't ever get any closer to each other. And in fact, they won't. These lines are parallel. Parallel lines have the same slope. Parallel lines are on the same plane, in this case the coordinate plane, and they never intersect. Well, what happens when you have two equations like these? How do you solve this system of equations? You don't solve it because it can't be solved. The question, what is the solution of this system of equations, has an answer. The answer is that there is no solution, because there is no one point that has coordinates that would make both equations true. This will happen every time you have parallel lines. So anytime you can't get a solution in a system of linear equations, and that will happen frequently, you need to know what's happened. You've You're dealing with parallel lines. They're not going to intersect. As soon as you discover that that's the case, stop. Don't waste your time with it anymore. You're not going to find a solution. The answer then is that there is no solution. So notice, there's no solution, but there is an answer. The answer is that there is no solution. Let's consider these two linear equations. They're in different forms, so we'll treat them differently. The one on the left is in standard form. That means that we can find the intercepts very easily. The intercepts are c over a for the x-intercept, and c over a would be 6 over 2, which is 3. So the x-intercept is 3, right here. The y-intercept is c over b, which is 6 over 3, which is 2. So the y-intercept is 2. There it is. There we go. So the line goes through those 2 points. It'll look like that. Now on the right-hand side, our slope has a y-intercept of 2. It looks like we might have already found our solution. They seem to intersect at 0, 2. But wait, there's more. The slope is negative 2/3. The rise is negative 2, and the run is 3. So if I rise negative 2 and run 3, I'm right back on the line here. At this point, they have the same y-intercept and they have the same x-intercept. How can that be? There's only one way it can be. These two equations are actually equations of the same line. This system of equations, then, has a solution everywhere that the two lines run. Every single point on the line is a solution. Well, lines have infinitely many points. So this particular system has infinitely many solutions. So if somebody asks you to solve a system of equations and you get this kind of result, you have to tell them there are infinitely many solutions. Tell them up front, because if they want a list, you're going to be busy for eternity. You can't list all of the solutions. What that person really needs to understand is they've given you two equations for exactly the same line. And that may have some interesting implications for the problem they had in mind. But this is the result. There isn't one answer for this one. The answer is that there are infinitely many solutions. And if you want a complete listing, you're probably going to have to talk to somebody who has a little more time on their hands. Okay, so let's recap the entire lesson. The first method you've learned in this lesson is graphing to solve systems of linear equations. The process for doing that is to graph the lines, then determine a possible solution. You determine that solution by trying to determine where the two lines intersect at one point. Once you think you've got a candidate for being a solution, you should check the solution. You check it by substituting it not into just one line, but into both lines, because a genuine solution makes both equations true. So you take your x and y coordinates from your possible solution and plug them in for x and y in each of the equations. If both equations turn out to be true, then you've got yourself a solution. If not, then your eyes are deceived. You may have to use another method to find your solution. It's also possible, especially with the problems that are contrived for you in this section, it's also possible that you've messed up one of your graphs. So you should always check that over too. When you follow this process, you must understand that there are three possible results. The first possible result is that there is one solution. And that solution would be the point where the two lines visibly intersect on your graph. The second possible answer is that there is no solution. This happens when the two lines are parallel. They're on the same plane, but they're going in the same direction. That means they're never going to intersect. Two lines that have the same slope are parallel. There'll be no solution when that happens. The third possible result is that there are infinitely many solutions. This is what happens when you start out with two equations that are actually representing the same line. So if you graph two lines and they're right on top of each other everywhere, you've got infinitely many solutions. So you have a three-step process with three possible results. Hope you find that helpful and useful. There are other ways to solve linear equations, systems of linear equations. This first one is very important to master before you go on to the others, because with the others, you have to kind of visualize what's going on in this lesson, even though the other methods are more algebraic, more mathematical in their methodology. It's important to get this part down first, though, so that you understand the basic framework of the problem and the possible solution, the possible answers to each problem.